in the vastness of the Milky Way, in a quiet corner of one of its spiral arms. Our solar system drifts through an environment that is anything but ordinary. For generations, astronomers assumed the Sun floated through a typical patch of interstellar space, a mixture of thin gas, dust, magnetic fields, and radiation, a place as unremarkable as any other. But as our instruments improved, as the map sharpened, and as space telescopes gathered deeper, cleaner data, a new picture emerged. A picture that revealed something unexpected, something immense, and something strangely beautiful. We are not drifting through ordinary space at all. We are inside a hollow, a vast, three-dimensional cavity carved directly into the interstellar medium, a bubble stretching nearly 1,000 light-years across. A bubble so enormous and so old that the Milky Way itself has reshaped around it. And yet, for most of human history, not a single person knew it was there. Only recently, through a combination of data from the Gaia mission, the Hubble Space Telescope, and detailed studies of cosmic dust and supernova remnants, did scientists begin to understand the true nature of this colossal structure, and the forces that created it. And as the evidence continued to mount, an astonishing question emerged. What happened here? What cosmic event had enough power to sweep aside the great clouds of gas and dust that once filled this region? What force could clear out a cavity so large, so empty, and so precise that it is visible in the movement of nearby stars? And perhaps most importantly, what does living inside this bubble mean for the Sun, for Earth, and for us? Tonight, we explore the mystery. We uncover the evidence, we trace the Sun's path through this strange region. We follow the clues left behind by dying stars, ancient shockwaves, and the intricate dance of gas and dust across millions of years. And at the end of this journey, we may begin to understand how this bubble shaped our cosmic neighborhood and why its story is far from over. For now, let us begin where all great mysteries begin, with what we can see, because the truth is, this bubble isn't immediately obvious. You cannot detect it by looking at images of the night sky. It doesn't glow, it doesn't shimmer, it doesn't announce itself. It was discovered through subtlety, through the faint fingerprints left in the light of distant stars. Fingerprints that reveal the space around us is unusually empty. Imagine taking a beam of light and sending it through the galaxy. Ordinarily, that light would pass through clouds of dust, tiny particles suspended between stars. The dust would scatter the light, dim it, redden it, distort it, but in some regions, the light remains strangely clean, too clean. Astronomers noticed sections of the sky where starlight behaved as if it had passed through far less material than expected, almost as though something had cleared the space out. At first, the idea seemed far-fetched. How could such a massive region be so empty? And how could we have missed it? But as star catalogs grew, as dust maps became more precise, a pattern began to emerge, a clear shape surrounding us. A cavity, a hollow, a bubble, the local bubble. Stretching roughly 1,000 light-years end to end, it is not merely a gap in the galactic medium, it is a shell, a structure with defined walls, wrapped around the Sun's current position. Its interior is filled with extremely thin, extremely hot gas, heated by events that occurred millions of years before the first humans walked the Earth. From the outside, the bubble appears carved into the galaxy like a vast wound, its outer boundary lined with dense molecular clouds. From the inside, it appears as an absence, an emptiness where substance should be. But once scientists accepted the bubble's existence, a new mystery emerged. Why is it here? For decades, theories came and went. Some speculated it was a relic of a single isolated explosion. Others proposed it might be the natural flow of galactic gas. But none of these explanations fit the data. The bubble was too large, too hot, too uniform, and too structured. It had to be carved by energy, by something violent, by something powerful enough to push aside entire clouds of gas weighing millions of times more than our Sun. There is only one force in the galaxy that can do such a thing: supernovae. The explosive deaths of massive stars capable of releasing more energy in a few seconds than our Sun will emit across its entire 10 billion-year lifespan. And so the question sharpened. Could multiple supernovae, maybe a dozen, maybe more, have detonated here long before the Sun arrived? And if so, what stars? Where did they originate? And when did they explode? As scientists search for answers, they followed the trail of the bubble's walls, the ridges of dense dust and gas that surround it like the fossilized edge of an ancient blast wave. These walls hold the story, they hold the clues, And as we trace their shape, their composition, and their position in space, we uncover a timeline reaching back millions of years. A timeline of destruction, a timeline of creation. A timeline written by stars long gone. Yet before we can understand the forces that created this bubble, we must understand its structure, its strange emptiness, its shape, and the reasons it remained hidden for so long. Because the bubble is not static, it is expanding. Slowly, steadily, its walls continued to push outward, evidence of energy still echoing through the interstellar medium. This expansion was one of the first clues that the bubble is not a passive, accidental void. But if you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data, an active relic of past violence, a structure still carrying momentum from ancient detonations. But perhaps the most surprising element of the story is this: the sun was not always inside this bubble. It has been here for only a small fraction of its life. To understand what that means, to understand how the sun arrived here, and to understand how its journey shaped Earth's own history, we must turn to the maps created by the Gaia spacecraft. Because in Gaia's unprecedented catalog of star motions, scientists uncovered something extraordinary, something no one expected. A group of stars, moving together, passing through the region where the bubble now exists. Millions of years ago, these stars are not random. They are siblings born from the same cluster. Many of them massive, many of them destined to explode as supernovae. And as researchers traced their paths backward through time, the evidence became clear. These stars passed through the region we now occupy. Just as one by one, their most massive members reached the ends of their lives, exploding, detonating, carving, until the space that once held clouds and cold gas was swept completely clean. And what remained is the bubble we live in today. This is where the story deepens, this is where the evidence converges, and this is where we begin to understand not just what the bubble is, but what it means for the sun, for the earth, and for the countless stars forming along its walls. We stand at the threshold of an extraordinary discovery, one that reshapes our knowledge of our galactic neighborhood, one that reveals how interconnected the Milky Way truly is, and one that shows that even here, in the quiet corner of our galaxy, we are living inside the aftermath of cosmic violence. Now, let us explore the evidence, let us follow the clues. Let us uncover the story of the bubble that surrounds us. And let us begin the journey into a mystery millions of years in the making. To understand how scientists revealed the enormous bubble enveloping our solar system, we must first look at how they mapped the space around us. And remarkably, they did not find the bubble by observing what is there, but by observing what isn't. In the late 20th century, astronomers noticed something unusual in their measurements of starlight. When light from distant stars passes through the galaxy, it gathers signatures from the dust and gas in its path. The dust darkens the light, it scatters it, and it shifts it toward the red end of the spectrum. This is expected, this is normal. But when teams compared stars spread across the sky, they found regions where the starlight had been altered far less than in surrounding areas, almost as if the light had traveled through a long, nearly empty tunnel free from the usual interstellar clutter. The pattern was puzzling. Stranger still was the fact that many of these unusually clear sightlines radiated outward from the solar system itself. At first, astronomers believed the data must be flawed. Maybe the maps were incomplete, maybe the dust wasn't evenly distributed, maybe the instruments were picking up something else entirely. But as more surveys were done, as instruments improved, as infrared dust maps from missions like CO and Planck grew more detailed, the patterns solidified. The emptiness wasn't an illusion. It was real, it had structure. The sun was embedded inside a hollow. But the true revelation came decades later, when a spacecraft launched by ESA would finally allow scientists to map the bubble in 3 dimensions. Gaia, a mission designed to track the positions, motions, temperatures, ages, and luminosities of more than 1 billion stars with unprecedented precision. When Gaia's data became available, astrophysicists began measuring the distances to stars along the boundary of the suspected bubble. They studied the color of the starlight to determine how much dust it had traveled through. They traced the motion of young stellar groups, and slowly, a detailed picture emerged. A cavity approximately 1,000 light-years across, nearly spherical, though not perfectly, with uneven walls made of dense molecular clouds, and within it, hot, diffuse gas at temperatures reaching 1,000,000 degrees. It was unlike anything astronomers had seen before. The shape was unmistakable, the precision undeniable. But this raised a far deeper question. What created this bubble? Even the most optimistic models of stellar winds, powerful streams of particles blown out by massive stars, were not strong enough to carve something of this scale. The energy required was enormous, but there is one cosmic event powerful enough, violent enough, and common enough in the galaxy's history to do exactly this. The explosive death of a massive star, a supernova. A single supernova releases an unimaginable amount of energy. It can sweep away vast clouds of gas, create shockwaves that travel hundreds of light years, and carve out cavities in the interstellar medium. But one supernova does not explain the local bubble. The cavity is too large, too uniform, too hot. This bubble demanded a chain of explosions, multiple massive stars dying over millions of years, each contributing to a widening cavity, each pushing the walls farther and farther outward. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. But where were those stars? Where were their remnants? What cluster produced them? And why were they concentrated in this specific region? To answer these questions, scientists turned again to Gaia's precision tracking. They traced the motions of nearby star clusters backward in time, watching where they would have been millions of years ago. And then, something remarkable appeared. A moving group of stars known as the Scorpius-Centaurus Association, a vast cluster of massive, hot, young stars had passed through the region where the local bubble now exists. These stars were born together, they moved together, and many of them were massive enough to explode as supernovae. As researchers simulated their past positions, they found that millions of years ago, the cluster had been directly inside the area now occupied by the bubble. Not one star, not two, but dozens of stars, many of them ticking time bombs. As this cluster drifted across the galaxy, its most massive members aged rapidly. They burned through their fuel, and eventually, they died. One by one, the largest stars detonated. Each explosion sent shockwaves surging outward, pushing aside gas and dust, scooping out material, heating the interior, and compressing matter along the growing walls. Over time, the effects accumulated. Shockwave after shockwave expanded the cavity, until it became the enormous bubble we inhabit today. This was the breakthrough moment. The model fit perfectly, but scientists needed more than movement patterns. They needed physical evidence, hard, measurable proof that supernovae had indeed occurred nearby in the recent geological past. That proof came from an unexpected place, the ocean floor. In the early 2000s, researchers studying sediment samples from the Pacific Ocean made a strange discovery. Atoms of iron, specifically a rare isotope known as iron-60, were found embedded in ancient layers of seafloor crust. Iron-60 does not form naturally on Earth. It has a half-life of just 2.6 million years. If it were older than that, it would have decayed away. The only known astrophysical source of iron-60 is a supernova. This meant that in the past few million years, at least one supernova had occurred close enough to Earth to deposit dust particles onto our planet. And as the data accumulated, multiple layers of iron-60 were found, indicating not one, but several nearby supernova events. The timing aligned perfectly with the bubble's estimated age. The evidence fit together like pieces of a cosmic puzzle. A star cluster drifting through the region. Multiple massive stars reaching the ends of their lives, exploding, sending waves of energy across interstellar space, carving a cavity, leaving isotopic fingerprints on Earth itself. And while the supernovae that carved this bubble occurred millions of years before humans existed, their echoes still shape the galactic environment we live in today. But here is where the mystery deepens even further. Because when scientists examined the sun's motion relative to the bubble, they uncovered something unexpected. The sun was not inside the bubble when it formed. It drifted into it later. This simple fact changes everything. It means the sun, and by extension, Earth, has not always been sheltered in this low-density environment. It means the history of our solar system is intimately tied to the movement of stars across the galaxy. And it means that the bubble's influence on our world began long after the bubble itself was created. How long has the sun been inside the bubble? What was the solar system like before entering it? And what does this mean for our future? To find those answers, we must follow the sun's path across millions of years. And as we do, the history of the Milky Way will unfold before us. A history written by drifting stars, dying giants, and the structures their deaths leave behind. A history that reveals the bubble around us is not just a curious feature, not just an empty shell, but a testament to the unimaginably powerful forces that shape our galaxy. And perhaps the most astonishing part is this: the story is still unfolding, the bubble is still expanding. The stars forming on its boundaries are still being born from the shockwaves of long-extinct giants. This is not merely a relic, it is a living structure, a cosmic echo that continues to influence the galaxy today. And now, we turn to the next chapter, the sun's journey into the bubble. A journey that will reshape everything we thought we knew about our place in the galaxy. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. To understand how the sun came to reside inside this vast cavity, we must look back across millions of years, tracing its path as it drifted through the changing landscape of the Milky Way. For although the sun feels stationary to us, it is anything but. Our star is on a continual voyage sailing through the galaxy at roughly 220 kilometers per second, orbiting the galactic center once every 230 million years. A single orbit, a galactic year, lasts longer than the age of the dinosaurs. During this long journey, the sun encounters regions of dense gas, areas of intense radiation, quiet interstellar fields, and occasionally, structures formed by events both ancient and violent. The local bubble is one such structure. Its origins lie in supernova explosions that happened long before the sun wandered into this region. The bubble formed as massive stars exploded one after another, creating shockwaves that swept aside the gas around them. When the sun was young, still surrounded by the leftover debris of the early solar system, this bubble did not yet exist. Over millions of years, the sun drifted along its galactic orbit, passing through regions filled with far denser gas than the empty cavity it currently inhabits. But around 5 million years ago, something changed. The sun crossed the boundary. Simulations created using Gaia's star mapping data show that the solar system approached the bubble slowly, drifting toward one of its edges. At first, the environment began to thin. Starlight passing near the sun revealed lower densities, weaker dust signatures, softer absorption lines. And then, the sun crossed through the boundary wall. The moment the solar system entered the local bubble, it became enveloped in gas thousands of times thinner than the material it had moved through previously. The heliosphere, the protective bubble generated by the sun's magnetic field, responded to this change. In denser regions, the heliosphere compresses under the pressure of interstellar gas. Inside the local bubble, with so little material pressing against it, the heliosphere expanded outward, becoming larger, rounder, and more symmetrical. This change altered how cosmic rays entered the solar system, how interstellar particles interacted with planetary magnetic fields, and how radiation moved through the space around Earth. But the sun did not simply remain in one place. It continued its journey, drifting deeper into the cavity. Today, the sun is not at the center of the local bubble, it is closer to one of the edges. As it continues to travel, it will eventually emerge again into a region of denser interstellar gas. But for now, Earth and the planets exist within this unusual, low-density environment created by events that occurred long before life on our world ever began. To picture this more clearly, imagine the sun's motion as a thread drawn across a vast cosmic tapestry. For millions of years, the thread weaves through regions of varying density and composition. Some of these regions influence the shape of the heliosphere. Some alter the influx of cosmic radiation, some mark boundaries formed by ancient stellar explosions. The local bubble is one of these regions, a particularly dramatic one. As the sun entered the bubble, scientists believe it may have encountered remnants of supernova material atoms that once belonged to the outer layers of dead stars. Among these remnants were the very iron-60 isotopes that ultimately settled on Earth's ocean floor. Some researchers suggest that the arrival of such particles could even be linked to long-term shifts in Earth's climate, though this remains an ongoing area of study. But even more fascinating is what we find at the bubble's boundary. The walls of the bubble, shaped by ancient shockwaves, have compressed the gas around them so intensely at these regions have become fertile grounds for new star formation. Astronomers examining the bubble's edges discovered that many of the nearby star-forming regions, including the Taurus and Ophiuchus molecular clouds, lie directly along the bubble's outer wall. This is not a coincidence. When supernova shockwaves collide with dense gas, they compress it. And when clouds become compressed, gravity takes over, causing the gas to collapse into new stars. In other words, the death of stars inside the bubble triggered the birth of stars at its boundary. It is a cycle repeated throughout the galaxy. Old stars die. Shockwaves sweep outward. Gas collapses. New stars emerge. The local bubble is not just a void, it is a cradle. A nursery where new generations of stars are still being born from the remnants of those that came before. This realization reshaped our understanding of star formation in our region of the Milky Way, but the implications did not stop there. As scientists examine the bubble in greater detail, they notice something even stranger. The local bubble is not alone. It is connected to other cavities, other bubbles, forming a vast honeycomb-like structure of empty regions across the galaxy. These cavities intersect, overlap, and merge, creating tunnels through which stars and gas can flow. This network of bubbles forms a skeletal framework of the galaxy's interstellar medium, a hidden architecture sculpted by the violent deaths of massive stars. The discovery suggests that many of the features we see in the Milky Way, its filaments, its ridges, even the distribution of younger star clusters, may be shaped not just by gravity, but by the shockwaves of supernovae. The local bubble itself appears to be merging with at least one other nearby cavity, the Luti bubble, likely created by the ancient explosion of another massive star or star cluster. This means our solar system is traveling through a dynamic, shifting environment, one shaped by bubbles colliding, walls compressing, and shockwaves traveling across the galaxy. But the most profound realization of all is that we are witnessing the aftermath of events that occurred long before the sun ever arrived. We are living inside a structure shaped by stars that no longer exist. We are traveling through the ruins of cosmic events that lit the Milky Way millions of years ago. And as our star continues its drift, we will eventually exit this cavity, just as we once entered it. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. What awaits the sun when it finally emerges, what lies beyond the bubble's edge, and how will the change in environment affect the solar system? These questions lead us deeper into the nature of galactic structure, and into the reason scientists believe these bubbles are not just remnants of ancient explosions, but fundamental components of the Milky Way's architecture. To understand the next phase of this story, we turn to the forces that shape the bubble itself, the supernovae that detonated within it, the timing of their explosions, and the evidence that allows us to reconstruct a sequence of events stretching back millions of years. Because within those explosions lies the answer to the bubble's origin. And within that origin lies the key to understanding our place within it. To continue this journey into the heart of our cosmic environment, we must now turn our attention to the forces that carved the local bubble itself, the supernova explosions, whose shockwaves reshaped the galaxy long before the sun drifted into this region. The evidence for these explosions is written into the very structure of the bubble's walls. When astronomers examine the boundary of the cavity, the dense clouds and ridges of interstellar dust that encircle us, they see a pattern that can only arise from violent expansion. The walls are thick and uneven, with compressed filaments of gas that bear the unmistakable fingerprint of a shockwave's passage. But how many supernovae were responsible, and when did they occur? To answer this, scientists reconstructed the past positions of stars in the Scorpius-Centaurus association, the cluster believed to be the bubble's architect. This cluster is home to many massive stars, bright, hot, short-lived giants that burn intensely and die young. By studying their ages, distances, and trajectories, researchers can estimate how many massive stars once belonged to this cluster, how long ago they died, and where in the galaxy they exploded. The results were astonishing. Between 14 and 20 massive stars are believed to have detonated within or near the region we now call the local bubble, spread across a period of roughly 10 to 20 million years. Not all of these supernovae exploded in precisely the same location, nor at the same time. Instead, they occurred sequentially, often tens of thousands of years apart. But each explosion added its energy to the expanding cavity, reheating it, enlarging it, and carving it ever deeper into the surrounding medium. In simulations, each explosion appears as a bright, expanding sphere, and when these spheres overlap, they create a combined cavity that is far larger than any single supernova could produce. This overlapping expansion is exactly what we see when we examine the local bubble today. During these explosions, enormous shockwaves surged outward into the galaxy. As they traveled, they swept away gas and dust, compressing material along the bubble-less boundary and heating the cavity's interior to temperatures of up to 1,000,000 degrees. This hot gas still fills the bubble today. It is so diffuse that you could travel billions of kilometers without encountering a single atom. Yet it remains surprisingly hot, an echo of the energy released by the supernovae that shaped this region. But beyond temperature and structure, there is chemical evidence as well. And it comes from a place few expected, the crust of our own planet. We return, for a moment, to the iron-60 discovered on the seafloor. This isotope offers one of the clearest signs that supernovae occurred nearby within the past few million years. Iron-60 cannot be produced by normal stellar processes and decays too rapidly to persist from Earth's formation. Its presence in multiple layers of ocean sediment implies not just one supernova but several. When compared to simulations of the bubble's expansion, these isotopic deposits align with periods when the solar system would have entered regions containing supernova debris. This means that as the Sun drifted through the galaxy long before it entered the bubble, it passed through clouds containing the remnants of dead stars. Some of those remnants settled onto Earth. This is direct physical evidence that the bubble's supernova history is more than a model. It is written into the geological record itself. But while the iron-60 confirms that supernovae occurred nearby, the question remains, what happened to the stars that created the bubble? Where are the remnants now? The massive stars that exploded within the Scorpius-Centaurus association left behind neutron stars, or in some cases, were completely destroyed. Their siblings, less massive stars that did not explode, continued moving through the galaxy. Today, the association exists in several broken segments: Upper Scorpius, Upper Centaurus Lupus, Lower Centaurus Crux, spread across hundreds of light years. These groups still contain young stars, some only a few million years old. But their supernova-capable siblings are gone. They died long ago. And their explosions shaped the space around them. As simulations trace these star groups backward in time, they align perfectly with the path and timing required to carve the local bubble. The evidence is overwhelming and consistent. The bubble did not form from a single ancient event. It is the cumulative result of consecutive deaths of massive stars from the same cluster. But there is a deeper layer to this story. For these explosions did not merely create a void, they triggered new creation as well. Remember the walls of the bubble, the dense molecular filaments that now form ridges around the cavity. These are not passive structures, they are star-forming regions. In the Taurus, Perseus, Ophiuchus, and Lupus clouds, astronomers have identified hundreds of young stars. These regions are filled with protostars, infant suns still wrapped in swirls of gas. They glow in infrared images, bright with the heat of their formation. And these newborn stars lie almost perfectly along the bubble's boundary. This is not a coincidence. When a supernova shockwave strikes a dense cloud, it compresses the gas, squeezing it until gravity takes over and the cloud collapses into new stars. The local bubbles also have undergone this process repeatedly. In essence, the bubble represents a fossil record of star birth and death, a chain reaction spanning millions of years. Old stars exploded, their shockwaves reshaped the galaxy, and their energy triggered the birth of entirely new stellar generations. Today, those young stars trace the bubble's edges like bright beads along an invisible boundary. This means the bubble is not only a remnant of destruction, it is a cosmic nursery. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. A cradle sculpted from the interstellar medium are the violent deaths of stars. And it continues to influence star formation even today. This discovery changed how astronomers understand the architecture of the Milky Way. It revealed that the galaxy is not a smooth distribution of gas and dust, but a tapestry woven by bubbles of all sizes and ages, each created by ancient supernovae. The local bubble is simply the one we happen to live in. And now that we know its origins, scientists begin asking new questions. How long will the solar system remain inside this cavity? What lies beyond the bubble's walls? And is the bubble itself stable or changing? The answers to these questions require deeper mapping, more powerful simulations, and a new understanding of how bubbles interact within the broader galactic environment. Because just as individual stars form from gas collapsing under gravity, so too do galactic structures form through the merging, overlapping, and evolution of these vast supernova-carved cavities. And as the Sun continues its long journey through the galaxy, it will not remain inside this bubble forever. It will exit, just as it once entered, but the timing, the direction, and the consequences of that crossing are questions scientists are only beginning to unravel. To continue this investigation, we must widen our view, moving beyond the local bubble alone and into the larger network of cavities that fill our galactic neighborhood. Because the local bubble is part of something much greater, a vast, interconnected web of hollows and shells that shape the very structure of our part of the Milky Way. As astronomers expanded their view beyond the local bubble, a striking realization took shape. Our bubble is not an isolated feature. It is part of a much larger structural network, a sprawling architecture of interconnected cavities carved by generations of ancient supernovae. For much of history, the Milky Way was imagined as a smooth sea of gas and dust, gently swirling around the galactic center. But as telescopes became more sophisticated and computers more powerful, a new picture emerged, one far more dynamic, fragmented, and sculpted by violence than anyone had anticipated. The galaxy is filled with bubbles, dozens, hundreds, perhaps thousands of them. Some large, some small, some fresh with heat from recent explosions. Others ancient, collapsing, merging, or slowly fading into the background. The local bubble is simply one of the clearest examples because we are inside it, but it is surrounded by many others. The nearest of these is one called Lu, a colossal cavity believed to have been carved by a supernova roughly 1 to 2 million years ago. Lu Pi is larger than the local bubble, and it sits adjacent to us like a neighboring chamber in a vast cosmic hive. And remarkably, there is evidence that the local bubble and Lu Pi are merging. Their walls appear to be touching, compressing, and in places, blending. This intersection forms a bridge between the two structures, a tunnel of lower density gas linking one cavity to another. The Sun itself may be drifting toward this boundary, moving from one cavity into the next as it continues its orbit around the galaxy. If true, this would mean the environment surrounding the solar system is slowly changing once again, just as it did 5 million years ago when the Sun entered the local bubble. But this leads to deeper and more profound questions. How do these bubbles form across the galaxy? How do they evolve? And why do they cluster together in certain regions? The answer lies in the life cycles of stars. Massive stars do not form alone. They form in groups, giant clusters born from the collapse of enormous molecular clouds. These clusters may produce dozens of massive stars, each destined to explode as a supernova. When such a cluster lives out its life, its explosions carve multiple overlapping bubbles. These bubbles merge, expand, and sometimes even collide with bubbles formed by neighboring clusters. Over millions of years, this process produces a honeycomb-like structure, a labyrinth of low-density cavities separated by walls of dense gas. This is the true structure of the galaxy's interstellar medium, a patchwork of voids and shells shaped by ancient stellar deaths. Computer simulations reveal that these cavities are not random, they tend to form networks. Long chains of interconnected hollows that drive the flow of gas across the galaxy, influence star formation patterns, and shape the structure of spiral arms. The local bubble is part of such a chain. It is believed to be connected not only to Lu Pi, but possibly to several other cavities, some of which are so large and diffuse that their boundaries are difficult to detect. As Gaia continues to map more stars and more regions of the galaxy, we are only beginning to uncover this grand architecture. That these bubbles do more than shape galactic structure, they also influence the conditions experienced by stars and their planets. As the Sun moves through different environments, the density of gas around it changes. This, in turn, affects the size and shape of the heliosphere, the magnetic bubble created by the solar wind. Inside a low-density cavity, like the local bubble, the heliosphere expands outward. This provides a wide shield, buffering the planets from cosmic rays. But in denser regions, the heliosphere compresses, allowing more cosmic rays to enter the inner solar system. These variations may have had subtle effects on Earth's climate across geological time. Some researchers argue that changes in cosmic ray influx could influence cloud cover or contribute to long-term climate patterns. While far from settled science, the possibility is intriguing. A reminder that Earth's environment is shaped not only by its own atmosphere and orbit, but by the galactic environment it drifts through. Another key implication relates to star formation. We now know that shockwaves from the supernovae that created the local bubble compressed gas along its walls. This compression was so intense that it triggered the birth of multiple star-forming regions: Taurus, Perseus, Ophiuchus, Lupus. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. These regions are not random. They are the children of the bubble born from the same forces that carved the cavity millions of years ago. This connection between supernova explosions, bubble formation, and star birth is a profound insight into how the galaxy evolves. It even suggests that the bubble itself is still influencing star formation today. But the implications extend further still. If bubbles carve the galaxy, and if star formation occurs preferentially along their boundaries, then perhaps the distribution of stars in the Milky Way is not governed solely by gravity and gas density, but also by the violent deaths of earlier generations of stars. This reframes our understanding of the Milky Way's spiral arms. They are not just patterns of gas compressed by density waves. They may be decorated with bubble walls, cosmic scars marking the locations of past explosions. Now we turn to a deeper mystery, one still being unraveled. As we map more bubbles, we find they are not isolated pockets, but nodes in an even larger cosmic structure that spans far beyond the Milky Way, a structure that reflects the way the universe organizes matter on the largest scales, a structure known as the cosmic web, and perhaps most astonishing of all, the same processes that shaped a local bubble on a 1,000 light-year scale appear to shape the cosmic web on a scale of hundreds of millions of light-years. Bubbles carved by supernovae, voids carved by galaxy clusters, walls of gas and dust, walls of galaxies and dark matter, patterns repeating, structures echoing one another across staggering scales. It is here at this remarkable intersection of the small and the immense that we begin to see the local bubble, not as an isolated curiosity, but as a small expression of a much grander, universal design. A design rooted in the birth and death of stars, a design shaped by force and emptiness, a design that has influenced our solar system, our planet, and perhaps even the emergence of life itself. The deeper we explore this structure, the clearer it becomes. We are not simply drifting through space. We are moving through a story, one that began long before the sun was born, and one that will continue long after it is gone. Now, in the final chapter of this journey, we step back, widen our view, and explore how this bubble fits into the vast cosmic architecture that surrounds us, and how our place within it may hold clues about our past, our future, and our existence itself. To truly understand the local bubble, we must step beyond its boundaries, beyond this single cavity carved by dying stars, and look outward at the structure of the galaxy itself. For the story of the local bubble is not just a story of our neighborhood. It is a story written across the Milky Way and echoed across the universe. When astronomers began to map the galaxy in greater detail, they discovered that the interstellar medium, the gas and dust between the stars, is not evenly distributed. It is shaped by turbulence, gravity, magnetic fields, and the explosive deaths of stars. In this chaotic competition of forces, bubbles emerge. They overlap, they merge, they collapse, they expand. And over millions of years, they weave a structure that resembles a cosmic honeycomb, a network of vast cavities surrounded by walls of dense gas, each cavity born from ancient explosions. This is the hidden architecture of our galaxy. And the local bubble is one chamber within this vast, invisible network. From above, it resembles a hollow carved out by fire, its edges rippled and uneven, like the walls of a cavern sculpted by heat. From within, it appears as emptiness, a void where something once existed and was swept away. But as we compare this structure to the largest patterns in the universe, an astonishing parallel emerges. Cosmologists studying the large-scale structure of the cosmos, the distribution of galaxies across billions of light-years, find a pattern remarkably similar to the structure we see on a much smaller scale within the Milky Way. The universe, too, is made of bubbles and walls. On the grandest scales, galaxies cluster along vast filaments of dark matter, forming intricate threads that stretch across hundreds of millions of light-years. Between these filaments lie enormous void regions where few galaxies exist. These cosmic voids are surrounded by walls of matter, just as the local bubble is surrounded by walls of gas. It is as though the universe is built from a fractal design, patterns repeating across scales so different that they seem unrelated. Stars carve bubbles, supernovae shape cavities. Gas collapses into new stars, galaxies cluster along filaments. Dark matter shapes the cosmic web, and between these structures lie voids, echoes of emptiness mirroring one another across space and time. The local bubble may be small compared to these grand structures, but it is part of the same story. A story of creation and destruction, expansion and collapse, absence and presence. And this brings us to a profound realization. We live inside a cosmic memory. The very space we move through is shaped by events that happened long before our star existed. We are surrounded by the remnants of explosions that illuminated the galaxy millions of years ago. The dust that settles onto Earth, the gas that shapes star formation, the young stars that glow at the bubble's edges. All of these are products of a chain reaction set in motion by stars we will never see. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data. The bubble we inhabit is not just a structure, it is a storybook. A record of stellar lives and deaths encoded into the geometry of space. And yet, this bubble will not last forever. As the Sun continues its long orbit around the galaxy, it will eventually drift out of this cavity and into a region of denser gas. This transition, the next boundary crossing, may occur within a few million years. When that happens, the heliosphere will contract, cosmic rays reaching Earth may increase. The environment around the solar system will change once again, just as it has before, just as it will again. But even this journey is part of a larger pattern, a pattern that has shaped Earth's climate, the evolution of life, and perhaps even the origins of complex organisms. Some researchers speculate that Earth's movement through regions of different density could influence mutation rates, could affect cloud formation, could alter long-term climate cycles. These ideas remain speculative, but they highlight a profound truth. The history of life on Earth is not isolated from the galaxy. It is intertwined with it. We are shaped not only by our sun and our planet, but by the environment our solar system sails through. The local bubble is part of that environment, a chapter in the long, cosmic journey of the Sun, a chapter carved by the deaths of massive stars, whose shockwaves shape the very space we inhabit. In the deep time of the galaxy, bubbles rise and fall like waves. Clusters form, stars ignite, shockwaves ripple upward, bubbles overlap and merge, and new generations of stars are born from the ashes of the old. And through all of this, our tiny world drifts, unaware of the vast battles raging around it, unaware of the giants whose final breaths carved out our celestial home. Yet today, we can see this history with clarity. We can trace the evolution of the bubble, we can map its boundaries, we can witness the star-forming regions along its walls. We can detect the isotopes left behind on our planet from ancient explosions. And through these clues, we can reconstruct a story that unfolds across tens of millions of years, a story of fire, a story of emptiness, a story of creation, a story of connection. And now, as we reflect on all that we have learned, we come to the emotional heart of this narrative. For in this immense cosmic architecture, in this delicate balance between destruction and creation lies, reminder of our place in the universe. We are small, we are fragile, we are temporary, but we are also part of something vast and continuous, something older than the Earth, older than the Sun, older even than the bubble that surrounds us. We are the inheritors of a cosmic legacy. The atoms in our bodies were forged in ancient stars. The environment we live in was sculpted by stellar explosions. The space we inhabit is a gift from events that occurred millions of years before life began. The local bubble is a reminder that creation and destruction are intertwined, that beauty can emerge from violence, that even the emptiest regions of space carry stories waiting to be uncovered. And so we end with this question, a question that reaches beyond science, beyond astronomy, beyond the bubble itself. Did the local bubble help create the conditions that allowed life on Earth to flourish? Or was our arrival here simply a matter of drifting into the right place at the right time? Perhaps the truth lies somewhere in between. What is certain is that our journey through the galaxy continues. The sun will move on, the bubble will fade, new bubbles will form, new stars will be born along their walls, and the universe will continue creating and destroying, weaving its patterns across unimaginable distances. But for now, we are here, inside a cosmic bubble carved by long-dead stars, living in the echo of their final breath, a reminder that even in the vast emptiness of space, we are surrounded by stories written in light, dust, and time, and maybe, just maybe, that is what makes our small corner of the universe so profoundly beautiful. If you're enjoying this investigation and want more deep, science-driven explorations of the universe, go ahead and subscribe. On this channel, every week, we uncover the real mysteries hidden in the data.